Hey students, welcome to another GeoGebra class. In this class, we'll be looking at linear functions and their graph, quadratic functions and their graph, cubic functions and their graphs, and then we'll finally talk about some trigonometric functions like the sine, the cosine, and then the tangent. All right, so I have customized my GeoGebra. So when you go to options and labeling, I've set it to new point only. And the purpose of this is to make the graph sheet more neater because GeoGebra will automatically name every point, line segment, line that is created on the graph sheet. But I don't want that. I want it to be more neater, so it doesn't have to name everything. And then when you come to the algebra side too, I have set my sort to object type rather than construction order to make it more organized for me. All right, so let's begin. Now, before we start, let's talk a little bit about sliders. So sliders will help us to visualize whatever that we are doing here, okay? It will help us to visualize the things we have on our graph sheet. So we are going to start by assigning values to M and C. So let's assign one to M, and then let's assign one also to C. Then now when we can insert, so we know that the standard form of a linear equation is y equals mx plus c mx plus c, and we have assigned m to 1, and then c also we've assigned 1 to c. So this is our equation, general form of equation of a line, and then we have our m and c here. So m is 1, c is 1, that's why we have it in this form, y equals x plus 1. So the purpose of this is to give us a slider. When you select m, you see that we get a slider for m, and this helps us to change the values of m without having to manually insert the values of m for m again and again and again. The slider helps us to change, having to change it manually again and again and again. The same thing applies to c. We have a slider for c, which helps us change the values of c without having to manually input them again and again and again. All right, so that's for sliders. Now back to linear functions and their graph. So we know that the general form is mx plus c, where m is the gradient and y is the intercept. Okay, so let's talk about the gradient first. We are saying that m is the gradient. Now the gradient is the slope, so it determines how slanted the line is and then how steep it is as well. Okay, so it tells us two things: how slanted it is and then how steep it is. So the gradient will have two things: it will have a value, that's the number itself, and then it will have a sign, whether it is positive or it is negative. So we need to know the purpose of all these things. So whether it is, when it is positive, what does it mean? When it is negative, what does it mean? When the number is small, close to 0, what does it mean? And then when the number is very large to very large, what does it mean? So here we can say that m, or the gradient m here, is 2. Okay, so it is positive and it is 2. It's a small number. So this is how it looks like. So the slope. So you see that when you move from left to right, the line is increasing. Okay, as you move from left to right, the line is increasing. And as I move further into the positives, you see that the line is still increasing, but it is getting, the steepness is getting more steep. Okay, and then as I move into the negative, you see that now as I move from left to right, the line is decreasing. Okay, and then as I move further and further away into very huge numbers, that if you don't consider the sign, see that it is also getting steeper and steeper and steeper. All right, so that gives us some information. That tells us that the sign will determine whether it will move, as we move from left to right, it will be decreasing or increasing. Okay, that's what the sign tells us. So when it is positive, then when you move from left to right, it will be increasing. And then when it is negative, when you move from left to right, it will be decreasing. Then the value tells us how slanted it is. So when the value is getting larger, the steepness also increases. And then as the value gets smaller, closer to 0, it's getting, the steepness decreases, and so when it is exactly at 0, there is no steepness at all. Okay, and therefore the line becomes parallel to the x-axis. Okay, now let us confirm indeed that m is indeed the gradient, because we are the ones saying that is the gradient. So now let's confirm that it is actually the gradient. To do that, we're going to use the slope function in GeoGebra. So slope, and our line is f. So slope of f, enter, and then this is it. So this a tells us the slope of the curve. Now look at GeoGebra is also calculating for this line. It's also equal to 1.7. And you should be able to calculate the slope of this line given in 2.2 minus y1 all over x2 minus x1. Or you can also do it y1 minus y2 over x1 minus x2. Just that when you pick y2 first, then the denominator also have x2 first. If you pick y1 first, the denominator also have x1 first. Okay, so that's how GeoGebra is calculating this slope by using 2 points, and it's getting 1.7. And that is the same value for the m. Now look at something. As I change the value of m, so that the slope is also changing. It is exactly the same value as m. Okay, the slope GeoGebra is calculating the same value of m. That is why we say m is the slope. So m is indeed the slope. Okay, so at 0, you get a horizontal line, and then as it gets larger and larger and larger, the number gets larger, the line also gets more steeper, and the gradient will also be increasing with respect to the steepness of the. So the gradient increases the steepness. Okay, as the gradient gets larger, the steepness, so the line also becomes very, very steep. Okay, so that is all about the gradient. Now we'll look at the C as well. So let's highlight this M, and let's highlight the C. Let's select the C. So what does the C tell us? We say the C is the y-intercept, or is the point where the line intersects the y-axis. Now to see this very clearly, let's use the intersection key. So we'll use the intersect function here, and then select the function f, and then the y-axis. So y-axis. And then when I hit enter, the point is created at the intersection. Okay, so this is the intersection. This is where the line intersects the y-axis. So if I move the value of C, you see that the point A, the y value for it is also the same as the value of C. So that's what we are saying, that C is the y-intercept. This is the point where the line intersects the y-axis. So as I move the slider, the y value here for A is also moving, and it is the same as the value of C. Okay, so you move C, A is also moving. So C determines the position of the curve, whether it's going to be above or below. Okay, the x-axis, whether the line will be above or below the x-axis. Okay. All right. So to continue, so that's the linear graphs. Okay. So the general form is mx plus c. M is the gradient, c is the y-intercept, and the gradient determines the how slanted the line will be and the steepness. So as you move from left to right, whether it is positive or negative, if it's positive, then as you move from left to right, the line will be increasing. Then as you move from left to right, if it is negative, then the line will be decreasing. All right, and then the C will determine whether the line will be above or below the x-axis, because it's where it intersects the y-axis. All right, so now let's move on to let's quadratic graphs. So for quadratic graph, we know that the general form of every quadratic graph is y equals ax squared plus bx plus c. So, ma. So we know that the general form of a quadratic equation is y equals ax squared plus bx plus c. So a quadratic equation is just a polynomial of degree 2. Okay, so just like we did for the line, we'll first insert some values for some constants, okay, and then we'll use it to get a general form of a quadratic equation. So so I'm going to create a constant a1, assign 1 to it, then create a constant b1, and then assign 1, and then create a c1, and then assign 1 to it as well. All right, so once that is done, we can now insert our line, our curve. So it's going to be a curve this time around. Quadratic is a curve. So a, that is a1, a1x squared. Okay, so this is how we write x squared in the latest form. Then plus bx, b1 x plus c, so c1. Okay, so this is the general form of a quadratic equation. When I hit enter, I'll get my curve here. Okay, so it's a conic. Now, just like we did for the GeoGebra graph, okay, A1, B1, C1, okay, and then we're going to look at how that the A1, okay, is the coefficient of the leading term, and the leading term is the A1 here is the coefficient of the leading term, okay, so C1 is the constant, just like we saw in line where we had y equals mx plus c, where c is the constant, we also have the same C1 here. So if we click on C1, we get a slider for C1. Now you realize that as I move C1 to, you see that the curve move whether it goes up or it goes down. And that was the same thing that was happening for the lines as well. So the same as it did in the linear graph, either upwards or downwards. So the constant, the purpose of the constant does not change. It's still the point at which the curve intersects the y-axis. So when I use the same intersection key here, as I use the same intersect function, and I select the curve, which is J, and then the y-axis, you see that we get a point here, and the value of that point B, the y value negative 2.9, the same value as the constant is the same value. So now it's at 2.2 and it's also at 2.2 here. So that's the purpose of the C. It moves the curve either up or down. Okay. So as I move B positive, you see that it's moving the curve horizontally. Okay, not moving the curve horizontally. So what this means is that if B is negative, it's moving the curve towards the right. Okay, so that's the purpose of B. Now let's look at the purpose of C. Of A, we've talked about C already. So the purpose of A1. So when I move A, you see that the curve is changing. Okay, so now here it was U-shaped, right? That was when it was positive. Now as I moved it towards the negative, the shape changed into an N shape. Okay, so that's the purpose of the A. That's the leading coefficient, the coefficient of the leading term. So as the coefficient of the leading term is positive, the quadratic is going to be a U-shaped. It's going to be U-shaped. Then as it is negative, it becomes N-shaped. Now when it is zero, look at this. When it is zero, what do we get? We get a line. We get a line. That makes sense because when A is zero, you realize that the leading term becomes zero. I mean, AX squared, so when A is zero, then the whole AX squared becomes zero. And then we are left with BX plus C. And then BX plus C is the form of a line, right? So what we get should be a line. And that's what we have here. We have a line here. And that's why if you want your function to be quadratic, then A cannot be zero. Okay, the coefficient of the leading term cannot be zero. So that it will be a quadratic. Then when it is positive, you get U-shaped. And when it is negative, you get N-shaped. Now we can do certain things like roots, where we can find the roots of this quadratic. So we can use the roots command here. So that's the first one. Then the function is j, so root of j, and then we get this point C and D, whose x values are the roots that we are looking for. So the roots is basically like the intersection of the curve to the x-axis. Okay, that will give you the root. The x values, they will give you the roots. And we know we can get three situations. The first one is we have complex roots. The other one is we have two real roots that are distinct, and then the last one is that we have real roots but they are the same. We have they are equal roots. Okay, so those are the scenarios, and those scenarios can be tested here. We can move our curve such that it will show us the situation where we have the real roots, and so this one you see that the roots are real and then they are distinct. Okay, we have 0.29 here, 1.25 here. That's the point where the curve intersects the x-axis. So when we move the B, it's only changing the shape, as the roots are still real. Now let's select the C and let's see how the C influences the nature of the roots. So when I move C, realize that now it is changing completely. Okay, so we get to a point where we will have one root. So I'm trying to get that, but when C moves the curve above the x-axis, you realize that now the C and D here in the algebra view shows question mark, question mark. Okay, that's why it's showing question mark. So there's no intersection. The curve does not intersect the x-axis, so there's no values to record. That's why it's showing this way. It gets very close, and then you see that it will have one point of intersection. So that brings us to what we call the vertex. The vertex is the highest point on the curve, whether it is minimum or maximum. So in a U shape like this, the point here is the lowest point on the curve. So in this case, it will be a minimum. And then when A is moved such that we get an N shape, so when it goes into the negative and we get an N shape, then the vertex here, it will become a maximum to be the highest point of the curve. Now to see the vertex more clearly, we are going to use the turning point command. So we are going to use the turning point command to see the vertex clearly. Now the polynomial is J, so turning point of J, and then the vertex is created for us, so that's E, and then it occurs at 1.07, 2.31. That's the current state. Okay, that's where it occurs. So as I move the curve, the vertex will also be changing accordingly. Okay, so as I move the curve, the vertex will change. Now we need to know how, because the vertex is either a maximum or a minimum, right? And that is influenced by the leading coefficient A. So when I change B, it doesn't change the shape of the C. It only changes the position of the shape. It's only A that changes the shape of the curve. So it will give us this, which in this case the E here will be a minimum, and then when it is negative, we get this, which is a maximum. So this relationship is significant, and we can pick it out. So when the leading coefficient is negative, the coefficient of the leading term, sorry, when the coefficient of the leading term is negative, we will have the curve is going to have a maximum. When it is negative, it's going to have a maximum, and then when it is positive, we are going to have a minimum. This is going to be U-shaped, and they will have a minimum. So when it's negative, it's an N-shape, and we'll have a maximum. Okay. So that's quadratic functions, that's their graphs. Now we would like to also move on to cubic functions. Okay, so cubic functions also, they're also polynomials, but this time around their degree is 3. So let's clear this and then let's insert a cubic function. All right, so a cubic function, we know cubic functions are of the form ax cubed plus bx squared plus cx plus d, a constant d. Okay, so we'll first have to insert our variable so that we can use the slider. So let's insert our a, so a2, then b as well, b2, and then c as well, c2, and then d2. So now that we have those, now we can insert our cubic function y. So the general form is y equals a x cubed, then plus b x squared, then plus c plus cx plus d. And then this is our quadratic, our cubic function here. This is our cubic function, so that is h. H is our cubic function here. Or for the linear and quadratic, we can test the a2, b2 to see how they influence the cubic function. So when you select the a2 to get a slider for that, you see that now initially this cubic function is increasing here, and then it continues to increase. Okay, and that is when a was positive. That's the coefficient of the leading term was positive. So when I move it to the negative, you see that now it is decreasing, and then it continues to decrease. So it has now changed. First it was increasing and then increasing. Now it is decreasing and then decreasing. So the leading coefficient also changes the way the curve looks like. Okay, from increasing to decreasing. So when it's increased, now when it is 0, as we looked at when we're doing the quadratic one, when it is 0, it changes into what? A quadratic function. So we get a quadratic curve here. The same way for the quadratic, when the leading coefficient is the coefficient of the leading term is 0, we get a line for quadratic. Here too, for cubic functions, when the coefficient of the leading term, all right, so when it is negative, the shape changes, and then when it is positive too, it will change it from down, down to up. All right, now let's look at the influence of as I move b2, we can see what happens to b2. What happens to the graph as b, the graph changes in a very way. As it gets to positive, this part here, okay, this turning point here is more into the left. Okay, we have a major turning point in the left. Then when it goes into the negative side, this turning point here has moved to the right. Okay, so the graph of a cubic function. Now let's look at the way the c also affects it. So when I move c around, also c as you move it around, you see that the curve is changing. It has an influence on it. And then let's look at how d also has an influence on the curve. When I move d around also, the d is also the constant, right? And what have we talked about? What have we said about the constant? So the constant is the y-intercept. Okay, is the point where the curve intersects the y-axis. So you see that here, as I move this around, the point of intersection is also moving around. And to see it clearly, you can always use the intersect tool. You can use the intersect tool. The function is h, comma, and then the y-axis, and then we see the point of intersection f. So look at the value of f, the y is 0, negative 0.5, and that's the same value as the constant here. So for polynomials, the constant term is always showing us the point where the curve intersects the y-axis. Okay, and it will move the below the axis, move the curve horizontal. Okay, so for the constants, that's the purpose of the constant. They are the y above or below the x-axis. Is that okay? All right, so let's talk about the find. So we can do the same thing as we did here. We can do roots. We can do roots of h, and then it will find the roots of the cubic function for us. And then you can do other stuff too. Okay, so you can do the same class we did for the quadratic. We find the roots. You can do the roots here too. So the roots is where the curve intersects the x-axis, and therefore it will highlight this point here because this is the point of intersection of the curve and the x-axis. Okay, so that's the root of the cubic function. So we can do all that as well here with cubic functions as well. Now let's talk quickly about the trigonometric questions, and then we'll end the class. So for trigonometric functions, let me clear the graph. Now let's start with the sine of x. So for sine, an observation graph, it oscillates between 1 and -1. So the domain is the whole row of x from negative infinity to infinity. And then the range is from -1 and 1. Okay, so that's That's a graph of sine x. So you see here we have numbers. One, the x-axis is labeled based on numbers, -1, -2, -3. So if you don't want that and you want to see the sine and cos and tan, the trigonometry function, it deals with angles. So if you want to see angles rather than numbers, you can come to the settings here, then graphics, the graphics settings, then we'll come to the x-axis, and then you see units. Okay, so this unit is nothing here, so that's why you have numbers. So you can change it to pi. Then when you hit enter, it's going to affect it. 1, -1, and all that to pi. So now you can see we have pi, +2 pi, 3 pi, 1. Okay, so this is beneficial for sine because those ones deals with angles. So it's easier when you use the pi rather than using the numbers. All right. So let's move on. So from there, we can talk about the root. So we can also find the roots of this and then the turning point as well. Okay, so this sign is p. So let's find the roots of p. So when we find the roots of p, so we see we said the roots are the is a point where the curve or the line, so in this case the curve intersects um, the x-axis. Okay, so because sine oscillates between -1 and 1, a lot of intersection of this as it moves. Okay, so you see that there are a lot of points here, and these are not just the roots, there are more of them. So there are infinitely many roots as long as, because the domain is from -infinity to infinity, so it goes on and on and on. So that means the roots will also not end as the graph continues to intersect the x-axis as it moves. Okay, so these highlighted ones are highlighted because that highlighted them. That doesn't mean these are all the roots, there are more. Okay, so as you zoom out, you see that more and more points are shown. Okay, so that's how you get the roots of the sine function. The same can be done for cos and for tan as well. Okay, then we can also do the turning point of p, and then we see that the turning points have been highlighted too. So you see here, there's a turning point here, and then n, there's a turning point here. We have a turning point here. So the turning points have been highlighted as well. Okay, so let's look at cos as well. Let's look at how the graph of cos also looks like. So let's uncheck these. Let's look at the graph of cos. All right, so cos so y equals cos x. So this is the graph of cos x. So we can do the same thing for cos as well. We can find the roots. We can find the roots of kill, and then we get to all these points here. Those are the roots of kill, and then we can also do the turning point. Now, if you overlay the sine and the cos, you see a very interesting relation between the sine and the cos. You can see that it's like when you shift one of the function, okay, one of the graph of one of these functions, you get the other. Okay, so it looks like the sine graph is a shift of the cos graph, and the cos graph is a shift of the sine graph. They've shifted it a bit. Okay, so it's an interesting relationship between sine and cos, and it actually gives us a lot of properties, geometric identities. It gives us a lot of relating properties. Okay, so we can also visualize the graph of tan x, but the graph of tan x is actually a very interesting graph. You know that tan x is defined as cos. The graph of tan is defined as sine over cos. Okay, so we get a very interesting graph for tan x. Look at this. So we have some sort of waves or some sort of curves repeating itself again and again and again. And we can do the same thing as we've been doing. We can find the roots of that curve, of those curves. So root of r, and then you see that the roots will be highlighted for us. So once you know the root is the point where the curve intersects the y-axis, and you see that they've all been highlighted here for us. And then the graph of tan looks like this because tan is undefined. Because tan is defined as sine over cos. When cos is 0, the tangent is undefined. Okay, so this creates what we call asymptotes, vertical asymptotes at wherever cos x is 0. So when I do this and then I highlight the roots of cos, when I select the roots of cos, so we see that here this is the root of this is the cos graph, cos x, and these are the roots. This is where it intersects the x axis. So at this point, we have the vertical asymptote here, because at this point, the graph of cos x is equal to a point where the tangent is undefined. Okay, all right. So this is everything. This is what we are going to be doing today. When we go on, in our next class, we will look at more things that we can use the GeoGebra app to do. But for now, we'll end our class here, and then we'll continue in our next class. We'll look at more of the things that we can use the GeoGebra app to do. Okay, so thank you very much.